Okay, for record, all students are here. Okay, let's look at question number 4. How we apply the equation that we just learned just now. So if you look at question number 4, we state that a non-viscous incompressible fluid flow between a wedge shaped wall, which is given in the diagram below, into a small opening, and the velocity potential in the unit of meter square per second that approximately described in this flow is the velocity potential equal to -2 ln r. So we need to find the volume flow rate, which is our m, per unit length into the opening. Okay. So by looking at this diagram, we have x and y axis with the r, and we have our v velocity vr into the origin, and the angle here given by pi/6 radian. So you write the definition for your VR and V theta component. So VR equal to del phi or del velocity potential divided by del r, and your theta component is 1/r, and take the velocity potential component divided by the angle. Okay. You write these two equations, and then since you're given the potential equation, which is equal to -2 ln r, so you do the differentiation accordingly. All right. So if you differentiate your equation here, your velocity potential equation given by -2 ln r, you differentiate this one with del r, you will get you will get -2 divided by r. This is just a simple differentiation equation. And since in our equation we don't have theta here, so when you differentiate with theta, you'll get 0. Right? The flow rate per unit width q across the arc, this one, with the length of r pi divided by 6 arc length. So we know that circumference of circle equal to 2 pi r. So you only take this angle, pi/6 times r, you get the arc of length. Okay. So you integrate. You want to calculate the flow rate along the width of this one. So you integrate v times r d theta. All right, v r d theta. You integrate from 0 to pi divided by 6 radian. Okay. So you know that your VR just now equal to -2 divided by r. You substitute in. Right. Then you modify the equation. The small r become big R. Because we extend up to this point, the small r will become big R. So you cancel the r. You only get 2 d theta. Right, you simplify the equation, you get negative pi divided by 3. Use your calculator. 3.14 divided by 3, you get negative 1.05 m squared divided by s. A normal flow rate is m cubed over s. However, we're looking at flow rate per unit width. So we take out one of the m dimension. So we only have a small q, we only have m squared divided by s. Okay, so this is the answer for volume flow rate per unit length in the opening for this year. It's a negative 1.05 meters squared over s. Okay, so we have clear question number 4. We will continue to look at question number 5. So question number 5 is ask you to develop the velocity potential and the stream function for the free vortex in terms of circulation. So just now our flow is going up. Now we look at our flow is in the cylindrical direction. So if your flow is flowing in the circle form, we call it vortex, right? We call it vortex. Just now, what we learned just now is all going out, radial. So radial, we only have two kind of flow, which is either sink or source, depending on the m that we have. Okay. So just now we look at radial. Now we look at the vortex in the cylindrical pattern. So all the axis is still the same. It's only you see the V direction is a bit different. It's along the circle. It's along the circle, and every point of these are tangent to the circle. Tangent to the circle. It's one point here. This arrow is represent one of the point along the circle. So yep. And you have the potential, the streamline is constant. The velocity potential is constant. All right. Now to define a vortex, we use these two equations. So our velocity potential equal to k theta, meaning our velocity potential is constant in this mathematic relationship. K is a constant value, and our streamline equal to negative k ln r. Our streamline function, our stream function, equal to negative ln r. So if you look at this diagram, there's no velocity in the radial in the r component. There's no velocity coming out from along the r component. So our v sub r equal to 0. However, there's something on our theta component. So v theta equal to the definition 1 over r divided, take the stream function divided by theta, equal to negative partial differential of your stream function divided by r, equal to k divided by r. So this is a conversion from this term into this term, and then you use this relationship to do the differentiation. You'll get k divided by r. Okay. So we need to recall a rotational. So you'll see this diagram here. If you look at v theta equal to k divided by r, the relationship between v theta and r is 1 over r relationship. So you still get a curve without intersect on both axes. So mathematically, it will make no sense that the velocity will become infinity as it's near to 0. All right. So yeah, this is just a statement to say that the relationship between v theta and the r relationship. Okay. Now just now it's just an equation for vortex, your velocity, potential, and the streamline function. Now I look at the diagram below question 5, the two circle. I need to explain it a little bit because these two represent two different vortices. On the left, you have irrotational, or means to not rotate vortex. Irrotational or free vortex. On the left-hand side, on the right-hand side, you have a rotational or forced vortex. So sometimes in the question statement, you will see free vortex or you free forced vortex. Then you need to draw out or you need to understand how the particles behave inside the domain. Okay. Now, if you look at the diagram on the left, is on the free vortex. You will see that the v theta component and the r component, you see the solid line. This solid line represents the relationship of v theta equal to k divided by r. So you get a curve like that if you have a free vortex. However, for the forced vortex, you will have v theta equal to kr. You have a straight line, y equal to mx plus c. You get a straight line relationship, meaning that as you increase your r, your velocity component in the theta will be increased. However, for the free vortex, as you increase your r, your v theta component will be reduced. So it's a bit different between the two. Okay. So what happens if you put a stick inside this domain, inside the flow? What happened to the stick behavior? So on the left-hand side, the free vortex diagram here, let's say you have a stick with a cross here, you put at A, and then you let the flow to do the work. So as the stick move inside from position A to B, you will see that the stick of A, the stick will rotate a bit. You will rotate to this position. You see this stick here, the horizontal stick, it will rotate anti-clockwise to a certain position. So this is like 90 degree or 0 degree horizontal. But as your stick rotate to position B, you'll see that the body of the cross twists a bit. Okay, twist a bit. But if you refer to the diagram on the right, with the inside the force vortex, you see the cross sticks. What is the behavior from A to B? So actually, it do not do anything. It just maintain the orientation towards the center. Okay, so it do not rotate. The body do not rotate. It only continue to facing the center. On the left, the free vortex one, you see the stick will rotate anti-clockwise. The body will twist anti-clockwise a little bit. So there's a difference between left-hand side diagram and right-hand side diagram. Okay, so this one you can read from my slides later on. I just explain what is happening. Okay, now for the force vortex, For the force vortex, your V theta equal to KR, which is I just explained about this solid line. So the vortex motion is rotational and cannot be described with the equation of the velocity potential. Okay. So what happens if you combine these two? So if you combine these two, these two vortex, it's just you take these two diagrams combined together, all right? So it's just an answer for the blank that you have on your tutorial sheet. A combined vortex is one with the force vortex as a center core and a velocity distribution responding to that of a free vortex outside the core. And these are the equations that we will use. So R0 is R0 means at the center here, R0. So if you have a combined vortex, our equation V theta equal to K divided by R. So our R here must be more than R theta. The value of R below here, it must be more than here because mathematic model, it will tell you that as it's near to the center, you have an infinity value. So be careful if you want to calculate the combined vortex in calculation. Your R component here must more than the center, R center. Okay. So it means that in simulation, if your simulation can give you an illustration of the vortex, normally they will give you a very small R. They won't put 0 as R. They will use R 0.0001 in the calculation. Okay, so these are the limitation in mathematics model when you're using simulation software. Okay. Another equation that we use to calculate the V theta is that when you have omega, this rotational speed. So V theta in the angular motion, which is in the theta component, then you can use omega times R. And in this case, your R is less or equal to R theta, R0. Huh? So these two equations, you need to be careful on the region that you use. So if your R is more than R theta, R0, you use the one on the left. If your R, your interest area, your R is, you want to be inner of your R0 or less than R0, you will use the omega times R. So these are the two equations that you need to be careful on the region, on the R value that you use. Okay. The next one, we look at definition of the motion. We call it circulation. Circulation, there's a specific symbol with like half of the F without the horizontal component. Right, it's like a hook or like a X, huh? Like a hook symbol. The circulation is defined as a line that you see inside the diagram. It means that ds is the change of distance, v is the absolute velocity. So if you have all the points that have the same component of the velocity, then you combine all these points together, you get a line, and your velocity will move in circulation. So the mathematical model for circulation was given. Circulation equal to closed loop integration. So if your integration sign with the circle in the middle, it means closed loop. Means if you look at the diagram, it's closed loop. If you have a broken somewhere, then it's an open loop. So for circulation, we look at a closed loop cycle equal to V dot ds, means it's a dot product. V dot ds is a dot product. V dot ds. Then you get circulation. So mathematical model for irrotational flow or uniform flow, we have V equal to del inverted triangular times the velocity potential component. So you substitute inside the circulation equation, V replaced by del phi on the right hand side. You write V dot ds. So this equation gives you d phi. Your circulation equation reduced to integration of a closed loop cycle of d phi, or change of velocity potential component, equals 0. So when you have irrotational flow, your integration for circulation will be equal to 0. Okay, so we just establish the equation for circulation. So when you have an irrotational flow, the equation will be equal to 0. Stop me if you're not able to copy the speed. If I talk too fast, slow me down. Okay, there's a diagram just above question 6, which is the one that you see on the screen now. So for free vortex, your V theta equal to K divided by R. K is a constant value. So circulation around the circular path of radius R given by this equation. Circulation equal to integrate 0 to 2 pi, because one cycle have 2 pi radian. K divided by R times R d theta. You simplify this equation, you have 2 pi K, because R cancel. You integrate only d theta, so you have 2 pi K. So just a note that for irrotational circulation, it do not include the singular point that will be 0. So this is another equation when you are having in the free vortex. You are inside the free vortex component, free vortex circulation. All right, so all right, so this is the summary of what we learned just now. So we have for vortex, we have the vortex velocity potential in k theta, stream function equal to negative k ln. And if you look at circulation equation, give you by 2 pi k. and you substitute circulation in the velocity potential equation, in terms of velocity equation, then you will get, because of k, you substitute this, you rewrite the k in the circulation divided by 2 pi, substitute here, your velocity potential will be circulation divided by 2 pi theta. And for the stream function here also same, you rearrange this equation, substitute your k inside, you will get circulation divided by 2 pi ln r. So these two equation is for vortex calculation. Okay, next we look at example. This is question 6. So question 6 give you an example. So this is a vortex that you open the water, or you have a water bottle, you shake your water bottle, then you will see a vortex inside the bottle. This is a free body diagram of what is happening, cross section for the vortex. So it's just that on the surface of the water, you have atmospheric pressure, and you have a triangular just to say that this is your atmospheric pressure acting on station 1, station 2, and you have a x and y axis, reference axis. Your r is from the center of the axis towards this one. So later your equation will start from the center of z-axis, right? And then your original reference axis is at the surface. If you connect this horizontal line to another side, so your axis is at the middle of the reference position. So then another location we're going to use is your z sub s. Right, so it's just from the horizontal towards down. So what is the statement give us? So we need to drain the liquid from a large tank with a small opening. A vortex was formed, and you're given a velocity potential equation. Determine an expression relating the surface shape to the strength of the vortex in terms of circulation. So how do we solve this one? So we are given the velocity potential in pi equal to circulation divided by 2 pi theta. So since our case in the statement, then because we have an irrotational flow field, then we can use a Bernoulli equation. We did this one. So P divided by specific weight plus V squared divided by 2G plus Z. Same for the another side. 0.1 equal to 0.2. Okay, so this is a Bernoulli equation. Then because our flow is from a very big tank, so P1 and P2 are exposed to the atmospheric pressure. So it's 0, 0.1 and 0.2, 0. Then our Bernoulli equation is further reduced to V1 square divided by 2G. And you pull your Z component to the right, become negative. So you have V2 square divided by 2G plus Z2 minus Z1. Okay, Z2 minus Z1. So Z2 minus Z1 is your ZX. here. All right, Z2 minus Z1 is your Zx as shown in the diagram. So recall the V0, V theta equal to 1 over R del phi divided by del theta equal to circulation divided by 2 pi R. This velocity equation in the theta in the vortex equation. Again, our point 1 velocity equal to 0. At point 1, velocity equal to 0. So our equation just now, our Bernoulli equation further reduced. We don't have V1 component. So we only have negative V2 squared divided by 2G equal to Zs. Then you substitute the non-value here.
So
Yes.
in the formula one, right? The V1, the one beside the V1 over 2G, right? There's a plus sign, right?
It's a typo error. Just
the
ignore.
other side, right?
Yeah, just ignore this one. Yeah. It's a typo error. Okay. So if you substitute the velocity equation inside here, so you square, then you get your Zs equal to negative circulation square divided by 8 pi square R square. Which give you the equation for the surface profile. It means that this equation on the left, Zs is the difference of the elevation as is dropped from the surface. What happened to the circulation? So R square divided by 8 pi square R square. So it will tell you as you drop the R, what happened, and then what happened to the circulation pattern also. Negative means it's going down, right? It's going down or going bottom. Okay. Now, just now we only see single point. Single point, call it droplet. Okay, we go for 1 or 2 more slides, then we have a short break. All right, now on the diagram there, you will see that there's a two source or sink. If we have a 2 source or sink, then you have a droplet. You have a pair of source and sink, then the phenomena is called droplet. It was formed in a special way. Means you have one coming up and then one going down. Which is it's quite common for interior design, where you spray water you pump water from the pool, and then you have another suction area to collect water from the surface, then you'll form a droplet. A few equation, just copy down. For droplet, the stream function is given by this one. Stream function equal to negative m. Again, m is the volume flow rate, not mass. M is the volume flow rate, divided by 2 pi theta 1 minus theta 2. Theta 1 is given in the diagram. Theta 2 is given by the diagram. Then you can rewrite your equation, trigonometry relationship. When you have a tan theta, one angle minus one angle, you can write your equation in this form. This is a trigonometry equation. So if you have a constant value in front of two angle, and you have a tan relationship between the constant value and the angle, you can write in this way. So once you have this trigonometry equation, then you will further develop. So you rearrange this stream function equation, means 2 pi. You move the whole constant from the right to the left. You have a negative 2 pi stream function divided by m. And then you put in the tan on both sides, like this. Then if you refer to the trigonometry conversion or trigonometry cheat sheet, so tan angle 1 minus angle 2 given by this equation. Right, this one is in the calculus chapter. Right, tan theta 1 minus tan theta 2 divided by 1 plus tan theta 1 theta 2. Here to here, on the left to the further right, this is trigonometric conversion. Okay. And then we try to look at the diagram to define the tangent angle. So you know that angle 1 here, tan equal to r sine theta divided by r cos theta minus a. This is also under calculus, advanced trigonometry chapter. Because your angle is, you're using the dimension in front of the angle. Just copy these two equations. So tan theta 1 equal to r sine theta divided by r cos theta minus a. Then for the angle number 2 is you replace the negative to become positive because it's inside the reference distance from the center. Okay, so your tan theta 2 equal to r sine theta divided by r cos theta plus a. So there's a difference between tan theta 1 and tan theta 2 below the denominator. One is negative a, one is positive a. Okay, just continue with these two equations. Inside there, you rearrange because we want to put this equation in terms of r and a that we know inside our scenario. Because this trigonometry equation do not give us the a and r distance that we can use. to calculation. So we need to convert this equation into this form. So at the end, your tan theta 1 minus tan theta 2 will reduce to this form. So tan minus 2 pi, the stream function divided by m. Again, m is the volume flow rate per unit length, equal to, after you do all the conversion, you get 2ar sine theta divided by r squared minus a squared. So if you have time, you just go and do the derivation. But this is the results after a very lengthy steps. This is just a summary of the journey from this stage, substitution of this one, rearrange, you get this one. Okay, and you rearrange because you want to see what is the equation for stream function. So then you move from the left to right, you have -1, inverted tan angle. And then you move back the constant value in front the stream function. You get -m divided by 2 pi tan -1 and the results that you calculate using the R and A. Just a note for your revision, the R is a center location. R is from the center location between the source and scene, because A equal to A here. So if you have a 2A, you are referring to the center between the source and sink, and the radius is towards a point, P, towards the intersection point of this source and sink to get the angle theta 1 and theta 2. Okay. So I think we stop at question 7 here. We have a short break. Another 15 minutes breaks. Okay, we continue at 4:50. I stop the recording.